recording. 1804, he made an ascent to 23,000 feet. This was at one of the World Expositions, an exploit that set the altitude record for several decades. That was way back 2 centuries ago, more than 2 centuries ago. To better control lighter-than-air balloons, Gay-Lussac carried out several experiments on the properties of gases. In 1808, he discovered the law of combining volumes. And that law is as follows. At a given temperature and pressure, the volumes of gases that react with one another are ratios of small whole numbers. So if I'm going to react 1 liter of hydrogen with something, it's probably either going to react with 1 liter of something else, or 2 liters, or 3 liters. Small whole number ratios. If I react 1 liter, it's not going to react with 0.738 liters of something else. Okay? So for example, what he found was he took some hydrogen. He took 1 volume of hydrogen. Okay, you could say 1 liter, but it could be any volume. It could be 50 milliliters. And if he combined it with 1 liter of chlorine, those reacted completely. There was no leftover of either of them, and they got 2 volumes, or maybe 2 liters, of hydrogen chloride, HCl. 3 years later, Amedeo Avogadro, of number fame, interpreted Gay-Lussac's observation by proposing Avogadro's hypothesis. I'm going to put a star beside this because you are expected to know Avogadro's hypothesis. Know this. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So in 1 volume, let's just say this is very small volume, okay? We have 1 volume of hydrogen containing 1 molecule, H2. Because remember, hydrogen is one of which type of elements? Diatomic, Brinkel-Hoff, okay? Brinkel-Hoff. Okay, so we have H2, we have 1 volume of Cl2, and that produces 2 volumes of hydrogen chloride. And how many particles of hydrogen chloride did we get? Yeah, here we had 1 H2 molecule, we have 1 Cl2 molecule, and over here we got 2 HCl molecules. So the ratio between the molecules is 1 to 1 to 2, and the ratio between the volumes is 1 volume to 1 volume to 2 volumes. And what he managed to figure out from that was that he said equal volumes contain equal numbers of particles. So 1 volume containing 1 particle, a second volume that's the same would contain 1 particle. Okay? Now, these are obviously unrealistic because we don't have little volumes that contain a single molecule. That's crazy small, okay? But here's just a couple other examples of the same thing. If you take hydrogen So here we have two H2 molecules, and we have one O2 molecule, and you can see the volume here. This is 2 volumes. This is 1 volume. And we get 2 water molecules. And because we have twice the number of molecules, we're going to have twice the volumes. So we have a 2 to 1 to 2 molecule ratio. We have a 2 to 1 to 2 volume ratio. Now, just a quick preview of our next unit, Unit 6. If I was just to say hydrogen gas reacts with oxygen gas to give water. Do you guys remember how to balance that? Could you balance it? Right now, on the left-hand side, we have how many oxygens? 2. How many do we have on the right-hand side? Just 1. So let's multiply this by 2. Now we have 2 oxygens and 2 oxygens. How many hydrogens do we have on the right-hand side? 4 hydrogens, because 2 times 2 is 4. How many hydrogens over here? 2, so we would need to multiply this one by 2. That's just a little preview of our next unit. Now, what do I see here? I see a 2 to 1 to 2 ratio. Yes? So there's 2 hydrogen molecules for every 1 oxygen molecule, gives us 2 water molecules. And do you see why it has to be that way? I have to have 2 oxygens in my products. Yeah? Otherwise, if I didn't have 2 oxygens in my products, I would have either created oxygen or destroyed it. Can we ever create or destroy matter? No. And because I started with 1, 2, 3, 4 hydrogens, I also need to finish with 1, 2, 3, 4 hydrogens. And that's why we balance reactions. And that's what Unit 6 is going to be all about. Okay? Here's a picture. Here's a picture showing more molecules. In this one, we have 1, 2, 3, 4, 5, 6 molecules. Okay? And over here we have 1, 2, 3 oxygen molecules. Yes? So what's the ratio of molecules here? 6 to 3 is the same as 2 to 1. So 2 volumes to 1 volume to 2 volumes. If I have 2 volumes, how many water molecules should there be in here? 2 volumes contained 6 hydrogen molecules. So 2 volumes should also contain 6 water molecules. It doesn't matter what the molecule is. At this temperature and pressure, if I had 2 volumes, it would contain 6 oxygen molecules. If I had 2 volumes, it would contain 6 methanes, which is CH4, or ammonias, which is NH3. No matter what particle I put in there, I would have 6 molecules as long as it's a gas. Okay? So now, Avogadro's hypothesis means that if I have the same volume, I will have the same number of particles. Now, if I have 4 grams of helium, how many moles of helium is that? Go look on your periodic table. Okay. Okay. So we have 4 grams of helium. How many moles is that?
1.
It's 1 because look, if we see helium, what's down at the bottom? 4, that is our molar mass. And what is molar mass? It is the mass of how many moles? Mass of 1 mole. Is good? Okay. NH3, we have 15 grams of NH3. How many moles is that equal to? Oh, that shouldn't say 15 grams. It should say 17 grams. Oh my gosh, I'm so sorry. 17 grams. Otherwise, it's not fun. If it says 17 grams of NH3, how many moles of NH3 is that? 1, because nitrogen weighs 14 and hydrogen each weigh 1. So 14 plus 3 is 17. And then O2, because remember, oxygen is one of the diatomic gases. We have 32 grams of O2. How many moles is that? 1 mole of O2. It would be 2 moles of oxygen atoms. It's 1 mole of O2 molecules. Okay? Now, you can see that they each take up the same amount of space. And it just so happens that at 0 degrees Celsius and 1 atmosphere of pressure, 1 mole of particles takes up 22.4 liters of space. Not any particles, 1 mole of gas. And guess what that means? That means we have found our conversion factor between moles and liters of a gas. Okay? There are 22.4 liters of a gas per 1 mole. Now, are you expected to memorize that number? Yes. How can I make it easier for you? Sometimes people want to write 24.2, right? And you're like, where does the 4 go? I just can't remember. But it is as easy as 2 plus 2 equals 4. So it's 22.4, not 24.2, because 2 plus 4 does not equal 2, right? So 2 plus 2 equals 4, 22.4. Yes? Hopefully that'll help you remember it. And once again, the 1 goes with the mole, The one goes with the mole. The one goes with the mole. The one goes with the mole. Okay. So we good with that? All right. Now, remind me, molarity. Molarity also converts between liters and moles. Molarity, what do we use it for? Do we use it for gases? Solutions. So this is for gases, but molarity is for solutions. And molarity is the only one where the one does not go with the mole. Okay? Yeah, everything else, the one goes with the mole, but not for molarity. Okay? So you can see, here we have helium. This volume is 22.4 liters. As long as we are at 1 atmosphere of pressure and 0 degrees Celsius, so this is a 1 to 1 to 1 ratio. And I think, are we running out of time? We're running out of time. So finish, actually go to the end of this page. Okay, so numbers 1 through 5 or whatever the heck it is. For your homework, we'll finish talking about gases next day. Okay?